All right, so we are going to start by talking about measurements and how we can accurately represent those measurements to other scientists because we need to start acting like scientists. We need to start practicing as scientists. Okay, so let's start with a couple of terms you may have heard before: accuracy and precision. So you may have heard these terms before in other science classes, but let's review those definitions. So accuracy is how close your measurement is to the accepted value. So you can think of this as how correct are you in your experimentation and measurements. Precision is how close a series of measurements are. So as you repeat your measurements, because remember, science should be repeatable, so as you repeat those measurements, are they all very similar and very close together, or are you getting what seems like a random grouping of numbers? Okay, so accurate, how correct are you? Precise, how consistent are you? Is how you can think of those words. Okay, so let's look at this in a visual representation. I'm a visual person, so let's take a look at a visual representation. So the goal is to be both precise and accurate. So this square right here, that's your goal. Notice that all of the X's, those measurements, are very, very close together, and they are right on target, so they are also correct. Okay? Now it is possible to be precise but inaccurate. So you can be precise. Your measurements can be clustered very closely together and repeatable, but they're really far off from the target, so they are not correct. Okay, that is called systematic error when that happens. Okay, it is possible to be accurate, so most of your answers are very close to the answer while being imprecise. So they're spaced apart. They're not very close together, so you're not very repeatable there. And then, of course, you can be both imprecise and inaccurate. So your answers are not clustered very close together, so you're not repeatable, but also none of your answers are very close to accurate. Okay, so this is a good visual representation that's good to add to your notebook so you can refer back to it later. Now, since we can know whether we are accurate or not, we can calculate how accurate we are. And we do that by calculating our percent error. So how wrong are we? Okay, so this is our very first equation that we are learning in this class. So be sure to put this equation on an equation sheet. Okay, I highly recommend you have one page right near the front of your notebook. Either glue it into the front, or if you have a 3-ring binder, put it right in the front so we can grow this sheet as we go, and then later on in the semester when we have lots and lots and lots of different equations, you can refer back to this to find the correct one very quickly and easily. Okay, so to calculate your percent error, you're going to take your experimental value minus the literature value divided by the literature value times 100. Now notice on the top, we've got lines at the beginning and at the end. That means that we're taking the absolute value here. So even if when you subtract this, if that's a negative number, you drop that negative. Okay, so you just take that absolute value. All right, so the experimental value is your value. It's what you measured. The literature value is the correct answer. It's the accepted value that has been determined over hundreds and thousands and maybe even millions of different experiments. Okay? All right. So let's practice with this. So a student determines the density of a substance to be 1.40 grams per milliliter. Find the percent error if the accepted value of the density is 1.36 grams per milliliter. Okay, so we start by just plugging these numbers into the correct place. Okay, so the student's measured value is 1.4, so we plug that in. And then the accepted value or the literature value is 1.36, so we plug that into both locations. And then we simply do the math. So 1.4 minus 1.36 is 0.04 divide that by 1.36, multiply by 100, we get a percent error of 2.9%. So this is really good. As an experimenter, as a scientist, you want your percent error to be very, very low. So anything under 5% is absolutely excellent. So this student did a very good job in their experimentation of their measurement. So 2.9%. So take a moment, pause the video here, put this into your calculator, make sure that you get the same answer. If you cannot get this answer on your calculator, get into contact with me so we can work it out together, so we can figure out what's going on with the way you're typing it in or with the way your calculator works. Okay, so if you need help, just let me know so we can fix this problem early on right here in the beginning. Next, let's talk about significant figures, also known as sig figs. So that's what you'll be hearing me call them from now on. In chemistry and in physical science in general, sig figs is king. That's where it's at. You have to know your sig figs because they tell other scientists very important information about your data. So what are significant figures? Significant figures are used to indicate the precision of your measurement. So it communicates to other scientists how precise your experimentation was. Okay, so how do we record sig figs? Sig figs include all the known digits, so the ones that you know for sure, you are absolutely positively able to measure them, and it also includes a final estimated digit. So that last digit, you don't know it for sure. You estimated it. And so this lets other scientists know. It indicates that that last digit is an estimation. So it lets them know how precisely you measured. Okay, so let's do an example. Here at the bottom of my screen, I have this yellow paper clip, and we're going to measure it, and we're going to use sig figs. Okay, so let's pop up a ruler. Okay, so notice the ruler is in centimeters, so we know our unit. And I can tell for sure that this paperclip goes to 2 centimeters. Okay, that is a known figure. I can also tell that this paperclip goes to 1, 2, 3 of the smaller lines. For sure, 3 of them. So that is a known figure. Now, the end of this paperclip, it kind of falls right in between that 3rd and 4th line. And there aren't any smaller little tick marks for me to be able to count. So that means that I have to estimate approximately where it is in between these 2 lines. Okay, so I know it's 2 and 3, so 2.3. And it kind of looks halfway in between those next 2 lines for me. So my measurement is 2.35 centimeters. Okay, so looking at sig figs, I know that 2.3 is known values. And I know that that 5, that's an estimate. It's an estimation. So that tells me how precise we are. Okay? All right, so how do we count sig figs? How do we know what is significant and what isn't? Okay, when we count sig figs, we're going to count all the numbers in a value except for the following: leading zeros. When there are zeros in front of numbers, they don't count. They are not significant. They are simply placeholders. Okay, so zeros in the front do not count. Zeros behind do not count if there is no decimal. Okay, zeros behind when there is no decimal do not count. Now, if there's a decimal, now they count. Okay, so that one has that qualifier of with or without a decimal. Okay, so let's get some practice. Let's take a look. So you think about these, what you think the answer is before I tell it to you. Okay, so look at this first one, 23.50. Okay, so there is a 0 in the back, but there's a decimal. That decimal makes that 0 important. So all of these numbers count. This value has 4 sig figs. Okay, let's look at this one. There are no leading zeros. There are no trailing zeros. all numbers count. So this one has 3 sig figs. Okay, let's look at this one. All right, this one we have a 0 in the back, and there is no decimal. That means that this 0 does not count. It's just a placeholder. So this number has 3 sig figs. Okay. All right, let's take a look at this last one, 0.080. Okay. Now remember, zeros in the front never count. Those are placeholders, so those do not count. Those two are not significant. We have a 0 in the back, and we have a decimal. So because we have a decimal, the zeros in the back count. So this one has 2 sig figs. Okay? All right. If you do not understand this, get into contact with me so we can work it out together and we can make sure you understand it. Okay? Because every single problem you do this semester, your answer should have the correct number of sig figs. If not, you will lose partial credit. Okay, you won't lose all credit, just a little bit. In college, though, be prepared if you go into college, you decide to go that pathway and you take some chemistry classes. A lot of professors, you can do all your work correct. Everything can be perfect, but you have your answer with the wrong number of sig figs, they will count the entire problem wrong because you wrote one extra number or forgot one number. That made me really mad about college chemistry. So just be aware, okay? For me, I do want you to know it's important. So it is going to be part of your credit for a question, but you're not going to get the whole thing wrong if you accidentally mess up your sig figs. But they are important, so don't forget them. All right, what if we're calculating? How do we know how many sig figs our answer should have? The number with the fewest sig figs determines the sig figs in your answer. Okay, so you just match the numbers in the problem, whichever one has the least amount of sig figs, that's what you match. Okay, so let's look at an example. Okay, so if this is our problem, 13.91 times 23.3. And our calculator gives us 324.103. Okay, so how many sig figs should I have? Well, if we look at this first number, 13.91, well, there are no zeros to worry about, so all of these count. This one has 4 sig figs. Okay, if we look at this number, 23.3, no zeros to worry about. We count them all, so this one has 3 sig figs. Okay, so our answer needs to have whichever one is the least. Since this one has 3, that's the least, that's how many our answer should have. So we need to reduce the numbers here to 3 sig figs. Okay, 324. Now be careful because we got to follow rounding rules. Okay, so I need 3 digits. So I need to look at the 4th digit to determine, do I round up or do I round down? Okay, so star this in your notebook so you don't forget. If that number is from 0 to 4, you round down. Since ours is 1, we rounded down to 324. If this number is 5 to 9, you round up. Okay, so 0 to 4, round down. Otherwise, round up.